Boa tarde a todos. Good afternoon. I suppose I have to speak English or what? So, continuing our plenary talks, I have the pleasure to introduce Lucia Caporaso. Lucia is a Harvard PhD in 1993 under Joe Harris. Her thesis became a landmark in the field of moduli space of curves. During the years 92-93, she was a Sloan Fellow. In 93-97, she held the Benjamin Pierce Assistant Professorship at Harvard. In the years 97-2001, she was Assistant Professor at MIT. Since 2001, she's Professor at Università Roma Tre. She has often been invited as speaker in international meetings, such as the European Mathematical Congress, Budapest 96, the Congress of the Unione Matematica Italiana, Siena 2015, and the International Mathematical Congress, Rio, next year. She has been a visiting scholar in several institutions, such as MSRI, Nice, and Strasbourg. Her publication is spread in many important mathematical journals, such as Journal of American Mathematical Society, Invenciones, Compositio, Journal of Algebraic Geometry, Crele, Tams, etc., etc., etc. Among her collaborators are Joe Harris, Barry Major, Dan Abramovich, Maurício Cornalvo, Eduardo Cernesi, Eduardo Esteves, and Juliana Coelho. They're not here? Sorry. I said here present. I am pleased and honored to introduce Lucia, and also very happy that she has lately become interested in graph theory, probably not from the viewpoint of commutative algebra as I wish to.
Thank you very much. Can you hear me? So I'd like to thank Aaron for the introduction. I'd like to say that the first time I gave a lecture in this room, it was some 13 years ago, and it was in a conference in honor of Aaron Simis's birthday and Steve Kleiman's birthday. Maybe it was your 40th birthday? Yeah, I think it was your 40th birthday. So I was very, very honored then. I'm very honored now. And I'm very happy to be at IMPA, as always. Every time I come, it's a great pleasure. So thanks, the organizers, for inviting me. OK, so here is the title of my lecture, Moduli Spaces in Algebraic Geometry. Let me begin with the main moduli space, the first one to be considered. In fact, you see the name of Riemann over there. The moduli space of smooth curves, connected and compact. For the experts, the word compact is a synonym for projective. And the moduli space is a funny word. You should think of moduli as a synonym for equivalence classes, isomorphism classes or equivalence classes. So that is a space for isomorphism classes of smooth curves of fixed genus over an algebraically closed field. It's a set, not only a set, it's an algebraic variety. Let me explain what that means. Of course, you may say, OK, it's an algebraic variety, so what? The point is that the structure of algebraic variety of MG as all moduli spaces in algebraic geometry, which is why moduli theory is one of the main areas of algebraic geometry, all moduli spaces in algebraic geometry are algebraic varieties themselves in such a way that the structure remembers how the varieties that parameterize move among each other and vary. So let me just make a simple drawing. So suppose we have a family of curves. So these are curves, one-dimensional varieties, parameterized by some base. This is the base, and this is the total space of the family that usually we denote like that. So to every point in B, you have a fiber, and the fiber is a curve. To say that MG is an algebraic variety is to say that associated to this data, there is a map, obviously a map, from B to MG that maps a point to the isomorphism class of the fiber. And that is not just a map, that is an algebraic map. That is a morphism of algebraic varieties. So this is called the moduli map of the given family. And it'll come back a little later of the family. Again, a point goes to the isomorphism class of the fiber over it. So in my slides, I used the following rule. Everything which is written in red is either a theorem or several theorems. Okay? So to make things quick, I didn't write every time theorem due to blah, blah. I just wrote the thing in red. All right? So I hope you don't mind. So let's see at some examples. The first examples with the simplest possible field, the field of complex numbers, are the cases where the genus is 0. So there exists only one complex curve of genus 0, namely the Riemann sphere, so that space is a trivial point. If the genus is 1, we have a one-dimensional space of curves of genus 1, and in fact the moduli space is a copy of C. Things get more interesting for genus 2, where you see we have a three-dimensional space quotiented by a finite group. This is a symmetric group on 6 elements. So let's focus on the case genus 2. From the algebraic point of view, we have a three-dimensional families of algebraic curves supported on the following topological space. Of course, this is over the complex numbers. So this is a compact surface, a compact orientable surface of genus 2. There's only one up to homeomorphism, but on this, we have a three-dimensional space of complex curves. Okay, so topologically is not interesting. Algebraically is very interesting. Now, from the examples already I wrote here, the first, the second, and third, we see that our moduli space is not compact, except, of course, the case genus 0. Why is it so? Well, it's not hard to convince yourself that if you take the family of all curves of genus at least 1, and that you see that as an algebraic variety, so it has a structure that tells you how your curves vary. For example, you can do the following. Look at this. Let's consider this cycle, and let's shrink it. We shrink it. That is a family. That is a perfectly honest family, which will correspond to some locus inside the moduli space of stable curves M2. But when this shrinks, when it becomes a point, then what you get is something like that. That is two tori, two genus 1 surfaces attached at a point, and that's certainly not that's not a smooth algebraic curve. This is why we have this statement that MG is not compact. And of course, why did I write it in red? Well, you have to prove that this thing cannot be avoided, which is not something easy. You can do that. It's a topological argument to show that there's no way you can avoid singular degenerations. Now, as we know, not just algebraic geometers, many other geometers don't like to work with spaces that are not compact. So when you find a space that is not compact, the first thing you try to do is to compactify it in a suitable, in a good way. So in my example already, you see that it makes sense. I actually picked it, of course, for future purposes. I picked this example because I want to suggest that to compactify, so to add boundary points to MG to get something compact, we have to add things like that. Or also, just so that you don't think I'm being biased, one cycle, but there's also this cycle. They're topologically very different. What happens if I shrink that cycle? If I shrink this cycle, I get a different type of object. I get something like that. With a hole remaining and something a little different. So this is another degeneration. All right, so this is just to introduce the compactification people have been studying for years, for decades. That is the moduli space of stable curves of genus G. I'm not telling you right away what is a stable curve of genus G. What I want to point out is this is a space, MG, which, as you will see in a moment, is compact, that contains MG as a dense subset, open subset, and it has a new feature that we didn't see before. To every stable curve, before you see, I made the point that a smooth curve has all smooth curves of the same genus have the same topological type. Now, when we compactify it, we add curves with interesting topological type, which we will denote by gx. This is the topological type of x. I will explain what that is in a moment, which is called a dual graph, but it is nothing but the topological type of x. In a moment, I will explain what that is, but the main thing is to every stable curve, we associate a graph, which, as Aaron said when he introduced me, I became interested in graphs recently. That's our first graph. All right, now, as I said, mg bar is a compact algebraic variety that has dimension 3g minus 3 if the genus is at least 2. Its construction, the main idea is due to the linear Mumford, but then the actual construction is due to Gieseker a few years later. I mean, not that just quite a few years later, in fact, 13 years later. And here is the official definition. You can read it, you can ignore it, it doesn't really matter. The main point is a curve is stable if it has only finitely many automorphisms and at most nodes as singularities. So these two curves I have here are stable. And then I have a second definition, the definition of a stable graph. A stable graph is a finite graph, vertices and edges, which has a weight function on the edges. And this is the stability condition. You can just read it. Every vertex of weight 0 has degree at least 3. Let me just give you, so now, how is a stable graph associated to a stable curve? For example, let's look at this. The rule is the following. I didn't write it there because this is something well known. I hope you forgive me for that, but I will do it on the board. The rule is the following. To every reducible component of the curve, there corresponds a vertex. So here we have two components. A component is just a complete subcurve in the curve. We have two vertices. And the weight on the vertex is the genus, the geometric genus of the corresponding component. So these have genus 1, both of them. So we have a weight 1, 1. And then we have an edge between two vertices for every node between the two components. So in this case, the graph we associate to this curve is this graph, the G sub x that I had in the previous slide. In this other case, we have only one component, so only one vertex. The genus is 1. And we have one self node. So we have a loop. So these are two examples of stable graphs. This is old stuff, goes back to the linear Mumford. Let me explain here, let me put there a few more things to clean my conscience so that I'm happy. So a curve is stable if and only if its dual graph is stable, and the genus formula is this. And here I have two examples in genus 3, a stable graph and a non-stable graph. Why is this not stable? This is not stable because it has a vertex of weight 0. I forgot to say. My convention is that circles like that versus bullets like that always represent weight 0 vertices. All right, so this is not stable because you have a weight 0 vertex of degree 2. Now, it's more interesting to look at the corresponding curves. So here I have, again, the two graphs and the corresponding curves. By the way, to every graph, there always corresponds a family of curves having that as dual graph. There are always lots of curves having that as dual graphs. Now, this is the non-stable one. Remember that when I told you that in the definition of a stable curve, I said that a curve is stable if it has only nodes as singularities and finitely many automorphisms. So why does this guy have infinitely many automorphisms? Well, you see this copy of a Riemann sphere, of a sphere here, with two fixed points. So any automorphisms of this curve has to fix or permute these 2 points, but it's free to act as however it likes on this. And we know that to have an automorphism of P1 depends on 3 parameters. So here we only have 2 parameters. So you have infinitely many automorphisms of the curve just looking at this component. Okay, so this is a not stable curve. Okay, that's the example. And now let's enlarge our horizon, okay? We don't have only the moduli space of curves, but also we have the moduli space of curves with n marked points. These are, of course, infinitely many of them, countably many of them. They are also very important, and they are all related to one another as follows. So this is what? MGN is what? Let me work on this picture since I have it already with some color. So now I want to, this is the case of genus 2. And now I want to add some points. Let's say n equal 2 to simplify. That means that I don't only consider curves, but consider curves with 2 points, for example, like that are ordered, P1 and P2. P1, say, for example, P1 and P2, they could be on the same components. They could be on different components. That gives you 2 different curves. Same here. So this is the moduli space of stable curves of genus 2 with 2 marked points. And the corresponding graph, the dual graph, in the corresponding graph, the marked points are labeled by legs. Legs legs are edges with only one vertex. So, for example, here we'd have 2 legs like that, P1 and P2, and so on the other. So here we'd have 2. So this picture, the construction I described before, generalizes to this situation, and this is very important. I'm saying that just for, so that you know, that the reason why, and so these moduli spaces, there are infinitely many, as I said, of them. They're all related to a series of maps. The forgetful map that takes the moduli space of curves with n plus 1 points and forgets the last point. The so-called gluing map, this moduli space, this map takes the last 2 points and glues them to a node. And this gives you a curve of genus 1 more and only n 2 less marked points. And then a clutching morphism that is just taking a curve of genus G1 and a curve of genus G2 and attaches them just like that at the last marked point. I don't want to spend too much time on it because that won't matter, but what's important is that using these maps and this whole family, one can have a very good way, a nice, beautiful way of describing the cohomological and not only cohomological properties of MG bar and all its brothers. And that this setup was extremely fruitful when in the late 90s, actually not in the 90s, quantum cohomology came up, and then quantum field theory and quantum cohomology proceeded together, and a lot of progress was made looking at these moduli spaces as a family. And then the generating functions were used, and several enumerative problems were solved using these moduli spaces. That's all I want to say about them, and then I go back to MG bar. And now I want to talk about the stratification of MG bar. This will bring us to the main point, the main topic that I want to focus on, because the study of the moduli spaces of curves is extremely rich. There's a huge literature in various areas of algebraic geometry, arithmetic geometry. There's a huge, so it's a really big field. And what I want to focus today is a tiny part that has to do with combinatorial aspects, because they proved in recent years to be extremely intriguing and to bring up a lot of new connections between various areas of mathematics where moduli spaces are used, as you will see in maybe two or three slides. So for now, I said let's focus on the stratification. Here I have a new set. This is the set of stable graphs of genus G. It's a finite set, okay? I won't have time to describe an example, but it's easy to see that it is a finite set because we are taking stable graphs. And so we have a natural map from MG bar to the space of stable graphs that maps every curve to its dual graph. Nothing big. This was known to the linear Mumford, even though maybe they never brought it out. But this is trivial, essentially. But then note that for any graph here, the fiber of this map is an interesting algebraic variety of dimension given by the number of edges of the graph. And so we have this partition, even though here I use the word stratification, but that's for later. because the map sigma will be a stratification map, as I will explain later. Here we have a partition of mg bar given by loci of curves whose dual graph is given, a stable graph, and these are all varieties, very nice varieties that one can describe explicitly. Okay? Let me now, oops, so I went too fast. So as I said before, stable graphs form a finite set. So that's why people from the 60s, 70s on didn't really pay attention to this thing. I mean, they were just linguistic tools, as I think Manin said in a very beautiful paper. But then people more recently, with the development of tropical geometry, decided to consider graphs as moving objects, that is graphs, not just graphs, but metric graphs. So, you know, you have a graph. You can have a graph like this, for example. This is rigid, but let's just give every edge an integer, a length, say L, L1, L2, L3. And let's let them move. So this gives you a more interesting thing. This is what's called a tropical curve. A tropical curve is a graph together with lengths assigned to their edges. So this was the next slide. That's the definition. Now, the definition I have here is more refined than the original definition of Mikhalkin and Zharkov, because you see, I am saying that a tropical curve is a graph with a length function on the edges, but implicitly my graph is weighted, because I said my graphs will be weighted. So we also have weights on the vertices. This is due to Branetti-Meloviviani down here. And here is a question: why do we need a weight on the vertices? Actually, chronologically speaking, the answer is not the answer I will give you, I think. Branetti is not here, but Melo and Viviani are here, so they can deny what I just said. But the reason I think why they originally put the weights on the vertices is that they had in mind the dual graphs of stable curves, where it's very natural to add weights on the vertices. But then they themselves discovered that from the point of view of tropical geometry, this is absolutely necessary. Because if you consider families of tropical curves without weights on the vertices, then you get into pathologies like this one. For example, this is the same I have here. You have three. Suppose you take the first edge and the last edge, and let its length goes to 0. This gives you a curve like this. All right, this has genus 2, this has genus 2. Apparently, there are no problems. Indeed, there are no problems. But now let's have let's have this guy go to 0, and we have a new graph, you see, where L2 is gone, and this graph is genus 1. Yes, so the genus dropped. Again, you move this L1, you make it smaller and smaller, you end up with a graph of genus 0. This is very bad. Not only is it bad, but also note that not only has the genus dropped, but the stability is lost, because this graph and this graph and this graph is not stable. So they fixed that by adding a weight on the vertices, and then refine the concept of degeneration by taking the weights into account. And this is what happens. The picture is fixed. Now I changed the picture a bit. I put 1 and 1 on the vertices for reasons that are, you know, make the definition more clear. When the edge L3 goes to 0, you get a vertex which remembers the weights of the two edges of the two weights the edge was connecting. So the genus here, the weight of this vertex is 2. And then whenever you contract a loop, the contraction remembers that you are contracting a loop, again by adding a 1 for every loop to the vertex. And so in the final, if you look at this picture, this is a degeneration of tropical curves of genus 4, which makes perfect sense, and every curve in the picture is stable. All right, so then now note for a moment that this procedure, this contraction algorithm that I just defined for you, the one that was defined by the 3 authors before, is a purely combinatorial one. You didn't need the lengths on the edges to define it. So this enables us to define a structure of partially ordered set on the set of all graphs of genus G. Just by saying that a graph is greater than the other if 1 is an edge contraction of that. So let me now give an example explicitly. For example, suppose let's do the case of genus 2. So the simplest graph of genus 2, which is also the smallest under that ordering, will be drawn here, right? So it's just an edge, no edges, a vertex of weight 2. This is a weighted graph of genus 2. Then you have, now in this picture I will actually list all the stable graphs of genus 2. Then you have a graph like that. That's the same graph that we had on that curve. 2 edges, 2 vertices and 1 edge. And this graph. These are 2 graphs, 2 stable graphs. They are the same there. Okay? Okay, before I drew the legs. Now, in my partial ordering, let me use a color for the point corresponding to the graph. This is smaller or equal than this one because if you contract the edge, you get this. So you have, let me draw it this way. This is order with respect to this. Let me put an arrow like that. And the same is this, because if you contract this edge, you get that graph. Now what else is there? Where there is more, you can have a graph like that. Okay, an edge which is a loop, an edge which is not a loop, vertex of weight 0, vertex of weight 1. Now, this graph has 2 possible degenerations. You can contract this edge, and then you get to this graph. Or you can contract the loop, and the loop brings you to this graph. Of course, you have 2 of them, but never mind. And then here you have another graph, which is given by a vertex of weight 0 and 2 loops. And here you only have one type of degeneration because you can only contract one loop, and the only possible comparison with the partial ordering is the following. We have 2 more, and then we're done. We have a graph like this. And this one, again, you have 2 possible contractions. You can contract a loop, and if you contract a loop, you go here, or you can contract the bridge of that graph, and that brings you here. You have one final graph, which is the following. You have 2 vertices and 3 edges. All of these guys already appeared on the board. No, not that one. And again, here you only have one type of degeneration, so you have this. All right, this picture is the poset S2, SG2. So this is a picture of SG2. As trivial as it may look, no one had ever considered it. All right, so it's a completely very simple thing, and it came out of its interest became evident in the following. So here I wrote that this is a ranked poset structure on SG with a rank function. If you know what a rank function is, then you know what that sentence means. If you don't, you can just ignore it, okay? But this is a very interesting poset, and it is a ranked poset, and it will come in the applications. So let's go back to the moduli space of tropical curves, which I haven't introduced yet, but I'm doing it now. So tropical curves form a moduli space, which is a non-compact, normal in the sense of separation axioms of topology. It's a normal topological space, so it's Hausdorff and blah, blah, blah. It is not compact, and it has a compactification, which I just need to mention without focusing on it too much, because it will come at a marginal point in the sequel, but it has been compactified. Now, these statements are due to various people that I wrote them here. My contribution is a trifle, has to do with compactification, but what's really important is the work of Mikhalkin and the ones I have already quoted. So, and then we have, as before, a map that associates to a stratification map sigma that associates a tropical curve its underlying graph. And as before, the fibers of this map are interesting objects from a geometric point of view. There are all before. So this is a topological space made of quotients of cones glued to one another in an interesting way. So in particular what did I do? Let's stay here. In particular, for every G, I have an R orbifold of dimension equal to the rank of the graph. And so again, we have a stratification, a partition as we had it for mg bar, but this is not just a partition. This is governed by the poset structure of SG bar by this simple relation. In other words, the poset structure of the set of stable graphs corresponds to an actual stratification of the partition that I listed here. Okay, so this is a fact. And the same holds for mg bar. Exactly the same holds for mg bar. We have already seen this. This is now this map sigma is something that I can call stratification map, because indeed the same thing I had in the previous slide for mg trop, for the tropical moduli space, holds for mg bar. In other words, the poset structure of SG governs the poset of strata with respect to closures of strata. All right? So we have these analogies between these two moduli spaces that were discovered in the beginning of around 2010. And we want to know why. Of course, in mathematics, it happens all the time that you ask a question because you know the answer already, right? Especially in talks. And this is a talk. All right? So I know the answer. I'm very proud of that. So let me tell you what the answer is. Now this makes us... we need a detour to a different area of mathematics. So this is toric geometry. We have an object using toric geometry that enables us to associate to mg bar or the stack mg bar. Here, I didn't have time. If I had the time, I would correct this and get rid of the word stack because it's just intimidating, you know. But it doesn't really matter. You can ignore that this is a stack and think of it as a space. The technical reasons why I have stack here, I can explain later in private. But anyway, so we have a generalized extended cone complex associated to this moduli space. What that horrible phrase means, this is a linear space. It is an R linear space. So it's a cone is a real cone. Generalized means that you allow infinite rays, and extended means something else I don't want to get into, okay? But this is something that we can construct. It can be constructed using the black box of toroidal geometry. And so we have this theorem that this object that can be constructed by toroidal geometry and a lot of stack theory, to tell you the truth, is actually isomorphic as a linear space, as a cone complex to the moduli space of tropical curves. And see here I have a bar. We need the compactification of it, otherwise it won't work, which is the reason why I mentioned the compactification. But from our point of view, it's just a detail. It really is a detail, because there are no important mathematical ideas behind. It's just a way of making everything work. So why is that? Again, this is another question that I'm asking because I know the answer. And so the answer, after a lot of work, the answer is, well, in those years, this is between the 2010, 2015, there was this parallel proceeding of tropical geometry with non-Archimedean geometry. And so people were studying a thing that's called the analytification of mg bar, whatever that is, in the sense of Berkovich. The important part is that this is a new area of geometry. In fact, this guy, the analytification of a scheme is or a variety, actually it's better to say a scheme, is a locally compact Hausdorff topological space. So we are in a new category, the category of analytic spaces, whose points parameterize stable curves, small families of stable curves. And what happened, what people were studying in those years, is that there is always a canonical map between the analytification of a space and the tropicalization of a space. Here I used MG bar, but this is true for any space with a toroidal structure. The toroidal structure I didn't mention, but forgive me. All right. Again, why? So then we see what is this? What is this saying? This is saying that we have two ways of connecting the moduli space of tropical curves, the one constructed by people I mentioned before, to two objects connected to the moduli space of stable curves, that is the analytification and the skeleton. All right, so there must be a picture, there must be a diagram, and in fact that's the case, and this is the theorem that I want to briefly mention. Also, this is not so recent. But so the point is, we have a commutative diagram. The analytification map has the analytification of MG bar has the moduli space of tropical curves as a topological retraction. Because this is what it's saying. This rho is a topological retraction. I have already said that these two guys are isomorphism. This is the tropicalization map that was in the previous slide. This is a diagram that is commutative. And this diagram generalizes to the big family of all MG and bar that I mentioned before. And it is completely, it is functorial in the sense that it's compatible with all those maps we had before. Okay? So this is nice. This gives us a way of connecting algebraic geometry, non-Archimedean analytic geometry, and tropical geometry. It's not bad. And let me just say, so, I mean, I don't know, I always liked, this is maybe because maybe this is the reason why I'm an algebraic geometer. I always liked when different fields of mathematics intersect and connect to one another. So that's why I get so excited when I see these things. Maybe you won't, but that's me. All right, so this is the same as before. The only thing is that I added the stratification maps, the two maps to the module to the poset of stable graphs. So why did I do that? So this is the same diagram that was in the previous theorem. This is an obvious map that always exists from the analytification of a scheme to the scheme itself. It's a triviality. And these are the two stratification maps that I described before. So the reason why I put that on the board is that I want to focus on the stratification maps because that's where everything started. So this is precisely where everything started. We first realized that there was this dual stratification map between these two, and then constructed the whole thing, which is pretty heavy stuff. That uses a lot of technology. I mean, I couldn't possibly have written this paper without Dan Abramovich, which is one of the the leading experts on stacks. So there's a lot of technique. But then the final result is beautiful. Everybody can understand it. All right? So this is what I want to do for the rest of the talk. I want to focus on the stratification map, and I want to look at other moduli spaces. Actually, not many, not only because we don't have time. I mean, I would love to spend more time about speaking about various moduli spaces, but of course this cannot be done. There are so many moduli spaces in algebraic geometry with amazingly interesting geometry that this would take a very long time. But let's just focus on a few of them with the same problem in mind. Can we find for these spaces a combinatorially meaningful stratification, just like the one that we express for the moduli space of stable curves? And then maybe once we have that, we can try and prove a theorem containing connecting tropical geometry, non-Archimedean analytic geometry, and algebraic geometry. Since the starting point for MG bar was the combinatorial aspects, I want to investigate the combinatorial stratification. So, of course, that means combinatorially meaningful means that I don't want to produce a new combinatorial object. I want to look for something that's already there, combinatorially speaking. Graph theory, again, thanks for Aaron for saying that because it was perfect for this talk, just perfect. And then see if I can cook up from that something else, like a tropical moduli space, the analytification, and so on and so forth. And this turned out to be much harder than what I thought first. So let's go on to different moduli spaces. So now I'm changing a little bit, but not that much. We will always be dealing with curves. But now, as you know, it's very hard to study curves without encountering their Jacobians. So here I have a smooth curve. Here I have its Jacobian. I remind you that the Jacobian of a curve is a principally polarized abelian variety. So it's a group. It's a projective. It's compact. So it's an abelian variety. It has a very rich structure from various points of view. For example, if the way I like to consider today the Jacobian is as the moduli space, pick 0, see, I forgot the word moduli space here, is the moduli space of divisors of degree Z up to linear equivalence. So this is itself a moduli space. Its points corresponds to divisors of degree 0 up to linear equivalence, or if you prefer, line bundles of degree 0 up to isomorphism, or if you prefer, torsion-free sheaves of degree 0 up to isomorphism. And this is one way of describing the Jacobian. 0 here stands for the degree. If you are over the complex numbers, as you probably know, this Jacobian is a torus, but indeed a very special torus, because not all tori are algebraic varieties. This is a torus, which is also an algebraic variety. This is hyperclassical theory. And a very classical theorem is the theorem of Torelli that tells you that the datum of a curve, of the isomorphism class of the curve, is the same as the datum of the polarized Jacobian. All right? So this is just to remind you that Jacobians really are important. And since they have such an interesting structure, for example, they're groups, studying them gives lots and lots of information about the curves themselves. I cannot possibly underestimate the importance of this, how that has influenced progress in the theory of curves in the previous century, okay? All right, now, abelian varieties, Jacobians, I said, are abelian varieties. They have a nice moduli space. That's denoted by AG. I wrote the name of Mumford here, but there are many other names that should go here. I had such a long list that I couldn't possibly pick. That Mumford is the first who constructed it as an algebraic variety, as far as I know. So it's an irreducible algebraic variety of that dimension, and again, it is not compact. It is not compact. And, okay, let's just take note of that. And let's look at the Torelli theorem under this new perspective, right? So we have a Torelli theorem that tells us that a curve is uniquely determined by its Jacobian. That is an abelian variety. And it is an abelian variety of dimension G, I forgot to say. So here, the Torelli theorem is restated by saying that there is a map from MG, the moduli space of smooth curves, to AG, mapping a curve to its Jacobian, and this map is an injection. And now we want to ask, this is something that has been asked by many people, if we can extend the Torelli map to the moduli space of stable curves. Now, it's easy to see that the answer is no way as it stands. It's not possible to define a map, to define a meaningful map from MG bar to AG. We need to compactify AG to do that, all right? And let me say why. Why is that? Well, one could say, okay, I take a stable curve, the moduli space of stable curves, I know what it is. I take the Jacobian of the stable curve. Jacobians are defined also for stable curves. Well, the point is that the Jacobian variety of a stable curve is not compact. So in particular, it's not an abelian variety. So it's not a point parameterized by that AG. So this is the first problem. So we want to, so indeed, compactifications of the Jacobian of a curve has been constructed in various ways by many people. And the point is that if you want to extend the Torelli map, we need to compactify the moduli space of abelian varieties using these compactifications. At least that's the goal we have. And so this has been done by various people. Let me draw the diagram. So the answer, the extension of the Torelli map exists and is not injective. So here I have some people that are listed in alphabetical orders. Really, it's just the actual chronological order should be completely different, but that doesn't really matter. So in those 10 years, people were studying the problem of compactifying Jacobians, and that was especially with me, Simpson and Esteves, defining theta divisor, and this is work of Esteves, and then compactifying the moduli space of abelian varieties in such a way that the Torelli map extends. And this is work of Alexeyev, the last. All right, so now we have an extension of the Torelli map from the moduli space of stable curves to the moduli space of abelian varieties, which sends a map to its compactified Jacobian in degree g minus 1. Let me just write one thing on the board. What do I mean by compactified Jacobian in degree g minus 1? Well, if x is smooth, if x is a smooth curve, then that pair over there is almost the same pair we had before. The only difference is instead of taking line bundles of degree 0, we take line bundles of degree g minus 1. That's the only difference. So this guy, this Jack x, is above is just the pair, pick g minus 1 of x, and the theta divisor translated to pick g minus 1. So this is the moduli space of line bundles of degree g minus 1 on the curve, or divisors or torsion-free sheaves, okay? So this is in case the curve is smooth. If the curve is not smooth, these are the compactified Jacobians I was mentioning before. They're pretty tricky objects. They're pretty tricky objects, but what's nice about them is that they fit into a family of varieties over the space mg bar. One for every d, because you have isomorphisms classes, you have line bundles of any degree. So now for every degree d, you have a compactified, you have a universal, so-called universal compactified Jacobian, whose fiber is the same guy I had in the previous slide. In particular, the fiber of this guy over a smooth curve is the moduli space of line bundles of degree d on that curve. That is this guy here, for any d. And the thing is that those guys are different from any d, as d varies. So we have finitely many models, but more than one model. So this PDG is a moduli space, of which I will not say because I don't have time, but it has a modular description. After all, the title of my talk was Moduli Spaces in Algebraic Geometry, so I have to highlight that every time it comes up. But I'm not going to tell you what this is a moduli space for. And for D, as D varies, you have different types. Finitely many altogether, but different types, which is why I insist on putting a D here. OK, now we have this compactification. We have this family of compactified Jacobians over mg bar. And how does this relate to the Torelli map? It relates to the Torelli map as follows. Here we have the Torelli map, the same I had before. Here we have the family in case g minus 1. And the point, the image of x in this space is the isomorphism class of the fiber of this. So tying in with what I said at the beginning of the lecture, in technical terms, the Torelli map is the moduli map of the family of the universal compactified Jacobian for degree g minus 1. So we have a Torelli map. Not only is it a Torelli map, a Torelli interesting map that has been studied with papers published in excellent journals, which I will not mention, but also it's a moduli map. That is, the image of a curve is the isomorphism class of the fiber of this family. All right, this was to tie in. Now let's go back to stratifications. All right, so I want to conclude by saying something about stratification. The main thing is I'm interested in these spaces, in these universal compactified Jacobians. That's what I want to study for today. And so let's see what we do. And there we are. So here I have a new guy. I hate when people do that. At the end of the lecture, they pull out a new definition. That's not an easy one. But I didn't find another way to do this, so I apologize. But here I have a new set. This OPG bar is a new poset, is a finite set with a partially ordered structure of classes of totally cyclic orientations on subgraphs of G. This is something that was already studied in graph theory. And with Filippo Viviani, we brought it out by discovering that that there is a stratification map of the compactified Jacobian in degree G minus 1, which I remind you is a moduli space, by this poset that I don't have time to describe, but it's totally cyclic orientations on subgraphs of the dual graph of G. It's a well-known thing in graph theory. And more recent, so this was a few years ago. More recently, we discovered, not this is with a different collaborator, I will say a few words later, that this stratification is induced by a more global, so here, see the difference here is, here I have the universal compactified Jacobian over the moduli space of stable curve. Here I have its fiber over a curve. So this is the local picture, this is the global picture. And so what we discovered is that there is a stratification of this guy using these posets that form a family over the poset of stable graphs, and everything is compatible with everything is compatible. So, and here is a huge diagram that I have, but it doesn't show up. It's so huge that it cannot be. All right, so this is the first result in the direction I was mentioning. So finding a stratification of the universal compactified Jacobian in degree G minus 1 with a graph theoretic meaning, that is this guy. You see, this guy has a canonical map onto the moduli space of stable graphs. Everything, all the maps in the exterior square are maps of posets, and the sigmas are stratification by ranked posets. So I'm becoming technical, but it's necessary. The two maps here are two surjections. This is the one we had before, the family of compactified Jacobians in degree G minus 1 over the moduli space of stable curves. This is the space of totally cyclic orientations for graphs of genus G, and this is the projection onto the graph. In the inner square, I'm just drawing, I have the curve, the dual graph, the compactified Jacobian, and the set of totally cyclic orientations. By the way, equivalence classes, there's a bar here because there's an equivalence, but let's forget that, for a graph. And now, so this is something that I proved just recently with Carl Christ, and what's more interesting, it's not more interesting, what's also interesting, it's perhaps more new indeed, but this didn't seem the right place to speak about this, is that we have a completely analogous diagram. So this is the same diagram as before, just the same. So no, don't worry. All right? So an analogous diagram exists in the case of degree G. Now, for the experts will know that the case of degree G versus degree G minus 1 is very important because it's the so-called Néron case. So it's one of the two most studied spaces, the space degree G minus 1 and the Néron case, for example, degree equal G, are the most studied spaces of these compactified Jacobians. So we could push that by using so-called rooted orientations on graphs, and this is a combinatorially technical term that doesn't make any sense to discuss here, but again, we discovered a combinatorially interesting structure on that. So also the moduli space PG bar has such a stratification. Now you will ask, of course, does that extend to every D? Now this time, I don't know the answer. We don't know the answer yet. We're working on it. But my hope is that one could find a general framework in which to define all these stratifications for all these moduli spaces and then find some rich structure among them connecting one another and connecting the various areas, combinatorics, tropical, non-Archimedean geometric. Okay? So, and I am done. I want to thank you very much for this beautiful conference. And I've been here every time. Every time I'm here, I see the huge, but many beautiful things. And there's one word in Portuguese that I can pronounce without embarrassment, and that's the following word.